Welcome to this session of notes. This is the last third of Unit 1 in AP Chemistry. And in this part of the unit, we are going to look specifically at solutions and reactions in aqueous solutions, how to make solutions, and how to calculate solution concentration by molarity. This set of notes will be mainly kind of delineating what is a solution and what is it not, and different factors that affect solubility of a solution or solubility of a solute in order to make a solution. So this flowchart may or may not be familiar to you, but it's used pretty frequently. So in this we look at the breakdown of matter. We have typically been focusing on pure substances, elements, and compounds. Pure substances are types of matter that are chemically combined and cannot be physically separated. Pure substances, as implied by the name, have a fixed composition. They have a formula. So their composition does not vary depending on the situation. If I'm talking about water, I'm always talking about H2O, 2 moles of hydrogen for every 1 mole of oxygen to make that formula. On the other hand, mixtures do have a variable composition, so their compositions are not fixed. Mixtures are physically put together, so you can therefore physically take them apart. So if I had, for example, air, the air that you're breathing right now is a mixture. It's a mixture of nitrogen gas and oxygen gas, some argon, and then some trace other elements in there. So mixtures typically are mixtures of compounds and elements, or mixtures of different mixtures put together. Mixtures can be divided into two broad categories: homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures to your eye look like they are evenly blended. On the molecular level, you would see some differences in there, but we look at macroscopically, what do we see? It looks like an evenly blended solution. Think Kool-Aid or lemonade made from a powder concentrate. When you take a sip of that, you don't want to taste any grit in there. So you want your mixture, your homogeneous mixture, to be evenly blended throughout. So homogeneous mixtures are not just liquid solutions. You can also have, as I previously mentioned, gas solutions where you have one gas dissolved in another. If you ever drink a soft drink, that's a gas dissolved in a liquid. And then alloys are pretty important solid solutions. So if you're talking about steel, steel is a mixture of predominantly iron mixed with carbon. Carbon strengthens that iron, and you get a much more durable metal with which to build. Heterogeneous mixtures, on the other hand, are not evenly blended. So you can see the different components in a heterogeneous mixture. If you think about a pizza or Italian salad dressing or orange juice with pulp, a lot of the powdered medications that you maybe took as a child, like amoxicillin, where you had to shake that before you took it, those are heterogeneous mixtures because eventually the particles that are in them will settle out. So this chart shows in more of a linear fashion what's going on with the major differences between solutions, suspensions, and colloids. So we're going to focus on solutions, but for general knowledge, I'll talk about the suspensions and the colloids in this. So the best way to look at is a mixture, a solution, a suspension, or a colloid is by the particle size. You don't need to memorize these specific numbers, but you need to know relative sizes. So we say that the particles that make up a solution, and when I say particles, I'm talking about the solute. The solute is the part of the mixture that gets dissolved. The solvent is the part of the mixture that does the dissolving. It's what you put the solute in. So if you're making sweet tea, the sugar is your solute. It's what you put in to be dissolved. It's what gets dissolved. And then the solvent would be the water. It's what you put your solute in. So particle size, I'm talking about solute. Solutions have very small particles, suspensions very large, and colloids somewhere in the middle. With a solution, the particles do not settle out. With the suspension, they do settle out over time. So think about muddy water, or if you've ever had milk of magnesia. That's a really thick, chalky liquid. Eventually, if you let that sit, that'll settle out. If you make a precipitate in the lab, initially you have looks like a cloudy mixture, but if you let that precipitate sit long enough, then it will fall to the bottom. Colloids typically don't have particles that settle out. They're suspended in what's called the dispersion medium, and I'll show you an example of that in just a minute. Solutions, the particles are too small to be separated by filtration. Same thing with colloids. Particles are too small to be separated by filtration. But suspensions, on the other hand, because their particles are very large, a filter paper will stop them from passing through. So suspensions can be separated by filtration. The Tyndall effect occurs when you shine a beam of light through a mixture, and the particles in the mixture, the solute particles, are large enough to scatter or to disperse that light. And so because solutions have very small particles, they do not scatter light, so they don't show the Tyndall effect. Whereas suspensions and colloids, even though colloids particles aren't huge, they do have large enough particles to scatter the light. So if you think about fog as a colloid, if you think about if you're driving at night on a foggy night, it looks like your headlights are spreading out almost in a cone shape. That's the Tyndall effect. The water molecules in the fog are large enough to scatter that light. So some examples of solutions would be like salt dissolved in water. A suspension would be sand in water. The sand's not going to dissolve, it's going to fall to the bottom. Or if you have an oil and vinegar salad dressing, they're not going to be soluble within each other, so they'll separate out. Colloids are a little bit harder. It's a pretty big class of mixtures that you're looking at, but think about some food some food examples, and then examples around the house. So emulsions like milk and mayonnaise, aerosols like fog and dust, and then foams like soap and meringue. Marshmallows are an example of colloids. And this picture just kind of shows you broken down in a little bit different way the difference between a solution, a colloid, and a suspension. So I talked a minute ago about this, the Tyndall effect. So it's the scattering of light by colloid and suspension particles, or the solute that gets put in there. Solutions do not show the Tyndall effect. So you can see if you have a true solution, or if you have a colloid or a suspension, if you shine a beam of light through the container that the mixture is in, the light will pass right through the true solution. The solution's particles are not large enough to scatter that light, but if you have a colloid or suspension, the particles are large enough to scatter the light. So you'll see that that light being scattered. And then here's another example. So on the left in this file, you'd have a true solution. On the right, you would either have a colloid or a suspension, and this is probably a colloid, judging by the fact that you don't have large particles settling to the bottom of that vial. So if you want to pause me a sec, this would be a good time for you to just check and make sure that you know Um, if you're given a set of classifications or questions, can you classify the description as a solution, as a colloid, or a suspension, or is it none of those? Is it not a mixture? So pause me for a sec and just kind of go through these, and then I'll come back and go through the answers. Okay, so if we go through this, pure water is not any mixture at all. Pure water has a fixed composition, so it's not a mixture, it's actually a pure substance, and more specifically, it's a compound. Fruit juice, it says shake before serving, so remember suspensions. Um, if you've got to shake it up, that means particles are settling, they're falling to the bottom. So fruit juice that says has a label like shake before serving, that would be a suspension. Lemonade, as long as there are no undissolved particles in there, that would be a solution. Brass, this is important. Every year people ask me where's brass on the periodic table. It's not. Um, Brass is a solution. It is an alloy. It's a solid dissolved in a solid. So it's a solid-solid solution. And then fog, I talked about, that's a colloid. For your questions, contain particles that do not settle. That would be a solution, and also colloids. Colloids have particles that don't settle. Can be physically separated. All mixtures can be physically separated. So solutions, colloids, and suspensions here. Tyndall effect, only colloids and suspensions. Another term for a homogeneous or homogeneous mixture would be a solution, and a fixed composition, not a mixture. Remember, that would be pure substances are the only types of matter that have a fixed composition. So true solutions are homogeneous mixtures. The solute is the substance that is being dissolved. So if you're asked about what the solute is in a solution, it's the substance that you put in to be dissolved. The solvent is the medium. It's what you put your solute into in order to be dissolved. If you have trouble deciding which one is the solute and which one is the solvent, the substance that is present in the greater amount is going to be the solvent. So in terms of types of solutions, on the left would be your solute, and on the right would be your solvent. So if you have a gas solution, like the air that you're breathing, oxygen is your solute. Actually, there's less oxygen in the air that you breathe than there is nitrogen. Nitrogen is the chief component. So oxygen would be your solute, nitrogen would be your solvent. If you're drinking a soda like a Coke or a Sprite, there's carbonic acid in there, which hopefully you know by now the carbonic acid is going to decompose into CO2 and water, but the fizziness in your drink, when you open that drink up, all that carbonic acid starts to decompose, so you get the bubbles, and the bubbles, that would be your carbon dioxide, solute, and then the water is your solvent. So that's a gas liquid solution. Vinegar is actually acetic acid dissolved in water, so that would be a liquid solution. Ocean water, and this needs to actually be flipped, so we'll just flip that. So ocean water, salt is your solid solute, and you put it into water, and water is your solvent. And then I talked about the alloy steel just a minute ago. So with steel, you have carbon put into iron. So just remember what an alloy is. It's a solid mixture, and it can be, but not always, a mixture of metals. And brass is another example of an alloy, a solid solution. And this picture is just showing you another example of, on the right side, of an alloy. A lot of the jewelry that you might wear, depending on the carat weight, gold is too malleable to be a sturdy piece of metal to be used for jewelry. So typically gold gets mixed with other stronger metals. So if you have a 14 karat gold ring, that is actually a mixture of gold and silver. So that's an example of an alloy. Um, there's also 14 karat gold with the mixture of silver, gold, and copper, and also an alloy there versus pure 24 karat gold, which is pure gold. It's more expensive. So sometimes you might run across the terms concentrated and dilute. So concentrated, both of these terms refer to how much solute is dissolved within a solvent. So concentrated means that you have a good amount, a large amount of solute relative to solvent, whereas dilute means not as much solute is dissolved in there. So just on a macroscopic level, if you're looking in the lab, concentrated solutions, concentrated aqueous solutions, especially if they have a color, tend to be much darker, whereas dilute solutions tend to be much lighter. And we'll see that in a lab that we do in about a week, where we look at the level of concentration of food dyes in Gatorade. So if you look at each of these on a particulate level, you'll notice that the blue dot is your solute particle and the purple dot is your solvent particle. So over here on the left in your concentrated solution, you have lots of blue solute particles, whereas on the right in your dilute solution, you don't have as many solute particles in there. So concentrated and dilute refer to the amount of solute dissolved in the solution. And this will become important. It's important now, but it'll become more important when we get to acids and bases, and we add two other terms, strong and weak. And sometimes people get dilute and concentrated confused with strong and weak. So we'll make sure we make that distinction again. And then this is just another view of dilute, concentrated, and we'll talk about saturated solution in just a minute. But you can read that chart there. So with solutions, we'll talk about solubility. The term solubility means how much solute can be dissolved in a given amount of solvent at a given temperature and pressure. So solubility is defined in terms of the amount of solvent, the temperature, and sometimes the pressure. It should always be defined as by pressure, but typically you keep it in terms of the amount of solute and the temperature of the amount of solute and the temperature conditions. So in terms of solubility, we look at three types of solutions. If a solute is soluble, then we can look at these three conditions. If a solute is insoluble, for example, I'm going to try to write with this. If we have calcium carbonate, that's bad, y'all, I'm sorry. If we have calcium carbonate, that's insoluble. So no matter what I do to it, it is not going to dissolve in solution. So when I talk about solubility in unsaturated and saturated and supersaturated, I'm talking about solutes that can be dissolved in water, that will not make precipitates in solution. So if you have a solution that's unsaturated, that means that you can still add more solute, and more solute will still dissolve. Saturated means that you've reached sort of a dynamic equilibrium, and we're going to get to equilibrium down the road, but it just means that if you the amount of solute that is being dissolved is in sort of a seesaw effect with the amount of solute that is coming out of solution. So you're kind of sitting in a pattern where you're at your max solubility. You can't add any more solute in. You kind of hit your threshold for the amount of solute that will be dissolved. Supersaturated breaks the rule of saturation. You have actually added in more than your max amount of solute. In order to make a supersaturated solution, you have to heat your solution to a very high temperature um, to get that extra solute to dissolve. Supersaturated solutions are cool because you can make them crystallize. All that extra solute that you had dissolved, you can get it to come back out of solution. So this picture shows, and I'll do this for you in class, but if you have sodium acetate, and sodium acetate, remember by your solubility rules, it's an ionic acetate, okay? So this is going to split into aqueous ions in this solution. So here is your sodium acetate supersaturated solution. If you add in a seed crystal, excuse me, so that's just all a seed crystal is just solid sodium acetate. If you add it into the beaker, then any extra sodium acetate that you put in here will start to come out because you are disrupting this extremely unstable supersaturated solution. Supersaturated solutions are very unstable. If you bump them, if you tap the surface like the table that they're on, then all that extra solute that you had dissolved and kind of broken the rules on dissolving, all of that extra solute will come out, and it'll come out quickly, and you'll get these really pretty crystals formed. So as the seed crystal is added, you'll start to see the excess sodium acetate crystallize and come out of the solution until you're back at your saturation level. So all of this extra sodium acetate came out of solution, and then this picture shows, okay, well now I'm back to a saturated solution. So any extra sodium acetate that I did add, it's not going to dissolve anymore. Okay, and then last thing, this is a solubility curve. This is a graph of solubility curves. And one thing I want you to notice is typically on the y-axis they'll have grams of solute per a given amount of solvent. In this case it's per 100 milliliters of water. And on the x-axis they'll give the temperature. So what I want you to notice is that for most, these are mainly ionic solutes. For most of these ionic solutes, as the temperature increases, so does the solubility. If you look at NH3, this is ammonia, this is a gas. So as the temperature of the solvent, water, increases, you'll notice that the ammonia gas actually becomes less and less and less soluble. So I want you to think about why that is, and we'll talk about the solubility of gases in class. But gases become less soluble when the temperature increases because it's harder for that gas to get in between those liquid molecules and to be dissolved when the liquid gets hot. The liquid just can't hold, the liquid molecules start to come apart from each other, so they just can't hold as much gas as they used to. And I think that's it for this recording. So watch this and let me know if you have any questions in class, and we'll keep going with some solution notes.